In this tutorial we will discuss energy conformation of alkanes. In the previous example we saw for butane, we draw a Newman projection where from the perspective of the observer we had a hydrogen pointing upwards for the front carbon and a methyl group pointing down to the right, while for the back carbon we had a hydrogen pointing downwards and a methyl group pointing up to the right. This is called a staggered conformation, and we have between carbon 2 and 3 a dihedral angle of 180 degrees. The question here we have to answer is if this conformation will be the most stable or if there are going to be other conformations that will be more stable. To answer that question, we're going to keep the front carbon stationary and we're going to rotate clockwise the back carbon. In that case, we're going to have a hydrogen up to the right, a methyl group pointing downwards and another hydrogen pointing up to the left, while if we continue rotating the molecule, we're going to have a hydrogen on the bottom, a methyl group on the top left, and another hydrogen on the top right. If we examine now the methyl groups, we will see that in the first case and in the case we have on the right, the methyl groups are close together and they experience steric repulsion, meaning that the electron clouds, they're going to repel each other. So this steric interaction between methyl groups is going to give us what we call Gauss conformation, and we're going to examine this with the conformation we have on the left, where the methyl groups are far away from each other and they don't experience steric repulsion. The conformation we have on the left is called Anti-Conformation, and it is the most stable by 3.8 kilojoule per mole compared to the Gauss steric repulsion. Up to now we have seen what happens in the case of staggered conformation, where we have a dihedral angle between carbon 2 and carbon 3 substituents equal to 180 degrees. Let's see now what happens in the case of eclipse conformations, where we have a dihedral angle of 0 degrees between carbon 2 and carbon 3 substituents. In that case, we're going to have an eclipsed hydrogen for the back carbon, an eclipsed methyl group pointing down to the right, and a hydrogen pointing down to the left, while if we rotate the back carbon, we're going to get a hydrogen eclipsed pointing up, another hydrogen eclipsed pointing down to the right, and a methyl group pointing down to the left, while if we continue rotating the back carbon, keeping the front carbon stationary, we're going to have a methyl group pointing up, a hydrogen pointing down to the right, and another hydrogen pointing down to the left. If we now calculate how much lower energy the staggered conformations have compared to the eclipse conformations, then we can calculate the torsional strain of each of the conformations by measuring the individual eclipsing interaction. In that case, we know that for hydrogen-hydrogen eclipsing interaction, we have 4 kilojoule per mole. For hydrogen-methyl eclipsing interaction, we have 6 kilojoule per mole. And for methyl-methyl interaction, where we have the eclipsing interaction plus the steric interaction, we have 11 kilojoule per mole. If we now calculate the total energy, the total higher energy of each of the eclipse conformations, then if we start from the energy conformation we have on the right, we have 4 plus 6 plus 6, then we go to 16 kilojoule per mole. And this is how much higher energy that eclipse conformation has compared to the one above, that is a staggered one. If we go to the structure we have on the left, we're gonna again calculate 4 for the eclipsing hydrogen plus 6 plus 6, then we go again to 16 kilojoule per mole, while for the one we have the methyl groups to be very close together and in an eclipsed conformation, we're gonna have 4 kilojoule per mole per each hydrogen, which means 8 in total, plus 11 for the methyl-methyl interaction. So in that case, we're gonna have 19 kilojoule per mole for the eclipse conformations where the methyl groups are gonna be very close. If we now see the energy diagram of butane, then we will notice that the eclipse conformation where the methyl groups are close together is 19 kilojoule per mole higher in energy compared to the anti-conformation where the methyl groups are far away. While between the staggered conformation, the anti-conformation is once again 3.8 kilojoule lower in energy compared to the one we have a Gauss interaction.